Well, thank you very much for the opportunity to give this talk. So I'll start with very general statements, and then we'll slowly move toward the anomalies. So if I am to summarize what flavor physics is in just one slide, I would say it's the following. So we see that there's a baryon asymmetry around us, which implies that there's more CP violation in the standard model. And what goes under the name of flavor measurements, that's a way to probe such new CP violating sources. And what I'll show in this introductory slides is that we're probing very high scales, or alternatively very small couplings. And beside that, of course, there's other benefits. So you potentially have some handles on dark matter or the strong CP problem. There are many experiments. What I collected here is there's a color coding that you can see. So the blue, it means operating experiments where at least part of the program is devoted to flavor physics. The gray one are the planned experiments. And then the green, which is many, are the EDM experiments of either the electron or the neutron or the proton EDM experiments. So many experiments translate to many measurements. If you open the PDG, there are many observables, and many of those, I would say, a big majority of those are related to flavor observables. So many rare decays. So there's branching ratios, angular distributions, CP violating asymmetries, and so on. So out of this really huge set of data, there are a few which are showing deviations from the standard model potentially. That's where we'll focus on in this talk. And the big question that we all have is whether this is a sign of new physics. All right, so before I go there, I will start with just general statements about why these observables are sensitive to new physics. And I'll split this into two small few slides, subsections. So what we're used to kind of hearing is that with these observables, you can probe heavy new physics. So that's through the offshore modes. I like to stress that you can also search for the light new physics. So this new physics states can be also produced in rare decays. And this will come in handy after we look at the anomalies. And then the big chunk of this talk will be covering the experimental anomalies. So I'll cover the G-2 of the muon, the B2S mu observables, and then the B2C tonion. And in each of those, I try to address what kind of new physics this could be if these discrepancies turn out to be really significant. And then finally, at the end of the talk, we'll look at what comes next. All right, so the intro into how you probe heavy new physics with the flavor observable. So the main tool relies on the following, that if you look at the processes where you're changing flavor, but not charge, so flavor changing neutral currents, at standard model, this conserved flavor. So if you have a gluon or a photon or a ZR Higgs, a process where you would change B to S, the three level are just not possible. They occur at one loop, which is shown here. While if you have new physics, you can have three level mediating flavor changing neutral currents. So that's where the synthesivity comes from, the loop suppression plus the CKM suppression that is present in the standard model, or the GIM suppression. All the contributions will scale as the coupling squared over the mass of new physics. If you integrate this guy out, this is, let's say, dimension 6 operator. So what you're really getting is some combination of couplings over the masses and the effects disappear either when the couplings are small or if the new physics is very heavy. Right? So how heavy? So let's say if I fix these couplings to be order 1, depending on the observable, you're probing scales which are, let's say, 10 to the 3 TeV to all the way 10 to the 6 TeV. So this green are the observables in the quark sector. Then the leptons, it's a similar story. Again, it depends on the flavor. And then the EDMs, the electron and the neutron EDMs, were again in 10 to the 5, 10 to the 6 TeV regime, again assuming order 1 coupling. And here, what's shown is the colored bars are where we are now, and this grayed out parts are the, let's say, 10 to 15 or maybe 20 years improvements, projections for the improvements on the reach. So you see that on the log scale, you can see big jumps on the sensitivity. And these big jumps on the log scale is not something that is just a future projections. This has been something that we've, as a community, achieved in the past decades. So for instance, what I'm showing here is I just looked at the quark transitions. Different colors are different systems. So KK bar, DD bar is the orange, B sub D mixing, B sub S mixing. And the different Wilson coefficients are just the chirality structures in the dimension 6 operators. So C1 is V minus A times V minus A, and then you change the chirality structure. And these arrows show the improvements that were achieved in, let's say, the last 15 years or so. So again, this it's a steady progress. Another thing that I want to imprint is that the projections are coming from increased precisions of the measurements, of course. So one way to visualize some of these are the standard CKM unitarity triangle. So this would be the CP violating parameter in the CKM. The fact that different measurements coincide is a sign of no deviations from the standard model, and it's just a subset of measurements, so that it's more easy to see what will happen. So this is just taking the LHCb measurements. If you go to the phase 1 upgrade, where it's already maybe hard to see, so you have to blow up, and then phase 2 upgrade, which corresponds to 300 inverse femtobarns of data, so that's about 30 times more than what they have now. And you see, I mean, this is getting ridiculously small. All right, so I said that I want to stress that it's not just the heavy new physics, but also the light new physics that you can probe through the rarity case. So as long as these are kinematically allowed, so let's say if I have a quark decay, everything is hadronized, of course, let's say B to S, if this particle is light enough, it will be produced on share, and then you search for either the missing signature or decay of this light particle. And in this way, you probe very small couplings. What I'll do is instead, so that we have, because we already have a reference from the heavy new physics, I will give you an example where this light guy is a PNGB, so that it couples to derivative operator, so that we have dimension 5 couplings, and we look at the scale. So just writing down the most general EFT operator, the PNGB will couple to quarks, leptons, and depending on what this global symmetry that was broken was, if this was flavor non-universal, there will be off-diagonal couplings. And in the next slide, I will have bounds on this capital F, which is just it absorbs the coefficients in the definition. Right? So the sensitivity of these flavor probes, I think what you want to compare this with is astrophysical probes to the diagonal couplings, for instance, to the photons. And we'll see that these are very much comparable, or even can be more sensitive. Again, depends on the flavor structure. So what I assume is that the couplings are just one, and then if you want to convert it to F, so small f, if you assume these couplings to be one, then capital F is small f. There are concrete examples of these PNGBs. For instance, you could have a QCD axion that is flavor violating, or even if it's connected to the flavor symmetry, then it carries a different name, oxyflavon. Or if it's connected with the lepton symmetry breaking, then it carries the name of Myron. All right, so let's see where we are. So focusing on quark transitions, the dark colors are bounds, present bounds on this capital F. So this capital F, as I said, absorbs in the definition the value of the coupling. And then V and A just tells me whether it's a vector or the axial coupling. And one thing that you notice, first of all, okay, the scales are even higher because now we're dealing with dimension 5 operators. There are many different probes, so I won't go over them. It depends on which flavor transition you look at. It can vary very much. The lightly shaded regions are the improvements, and in some cases, possible improvements in the future. And in some cases, these are really tremendous. The reason, for instance, in this particular case is that this was never searched for. So this would be B2 raw plus a missing energy was never searched for light, some light missing mass. And then the other thing to note is where the stellar constraints would be. So for instance, wide door cooling, that will give me a bound on the coupling to the electron. This is for QCD axions, so effectively massless, is up here, right? So really these flavor observers are in the same ballpark as this very stringent, it's a supernova, or the photon searches for axions coupling to photons are. All right, so so that was the introductory part, just to get us started. Now, what I'll do is I'll start talking about the experimental anomalies. So I'm really changing gears quite significantly. So the upshot is, so there's a selection of observables. There are not that few, but of course, there are still the order of 10-ish or so, where you see the anomalies. What's plotted here, so I stole this from Patrick Koppenberg. So what he did is this yellow or orangish points with the error bars. This is the standard model prediction. So you subtract the standard model. So all this is where all measurements should be. So you take the standard model prediction and you subtract the standard model prediction, so you get 0. And there's the theory error. Now it's the size of the error bar. So let's say, for instance, if I pick branching ratio B sub s to phi mu plus v minus, there's a big error, while R sub k, which is a ratio, the errors are small. The experimental data are here. So this is already normalized to the total error. So when I say that the theory error is small, it's small compared to the present experimental error. And these experimental errors are in blue lines. So in other words, the orange squared plus blue squared should give me one sigma. And we see that there are the 2 sigma-ish discrepancies, some are 3, and there's one guy here which is more than 4 sigma, right? Another thing to note is that, so they're grouped. all these observables up here have to do with muons and some quark transition B to S up to here, or just muons. The ones that have to do with taus are down here. Okay. All right. So what happened in the last year in this with these measurements? So psychologically, there was I would say there were two important measurements that came out in March, April this year. So R sub k, which is we'll see the ratio of B to S mu mu over the electron, went from 2.5 sigma to 3.1 sigma. So that's now the first measurement in the B anomalies that crosses this evidence threshold. Another important thing that happened is that there's slight tension in the B to S, B sub S to mu plus mu minus decays. Both of these observables are part of what I will call theoretically clean, so small theory errors. Then there are also theoretically dirty observables where you have to think more about the theoretical errors. And in here, the G minus 2 of the muon went from 3.7 sigma to 4.2 sigma in the discrepancy. And then for instance, this branching ratio for B sub S to phi mu plus mu minus, there's a 3.6 sigma discrepancy point. All right, so let's say if this is new physics, what would it mean? So I said there are two quark level transitions. One was B to C tau nu, and the other one is B to S mu plus mu minus. All right, so in the standard model, the two are either because of the three level W exchange, so it's a charge current that happens at three level, as some suppression because of VCB CKM element, but it's relatively minor. And then the B sub S to mu plus mu minus, it's a one loop induced process times the CKM suppressions. So if we interpret this as, let's say, some new physics that comes from a V minus A type operator, let's say, some couplings to the leptons, and I just put a 1 here instead of the coupling for the coupling, then this scale in the two cases, the new physics scale will be 3 TeV for the deviation on B to C tau mu, and 40 TeV for B to S mu plus mu minus. All right. Now, for G minus 2 of the muon, so this will come from the dimension 6 operator in SMEFT. So there's, let's see, if we put a Higgs wave there so that it's gauge invariant. So Higgs there, so you give a wave upstairs. Then the scale of new physics, again, with no suppression from the couplings, would be 15 TeV. Now here, you want to compare this 15 TeV with the constraints that are coming from, let's say, the flavor changing transition. So a cousin of G minus 2 of the muon would be mu to E gamma transition, where I just change the flavors here. So I will have a muon goes to an electron. And in this case, this suppression scale is 3,500 TeV. So any theory that explains G minus 2 needs to also account for the fact that there's no mu to E gamma discrepancy. All right, so what I'll do in the rest of this talk is go over each of these anomalies, about the experimental situation, and then what this implies for the theory explanation. So I'll start with G minus 2 of the muon, then I'll move on to B to S mu plus mu minus, Then we'll go to B to C tau nu, and then we'll try to sort of see if what happens if you try to connect one or two or all of these anomalies. All right, so G minus 2 of the muon. So here, I think the big question is whether we understand the standard model prediction. So there's an incredible effort by the theory community to understand the theory prediction. The main error comes from the hadronic vacuum polarization. So this type of diagrams on the left that's shown here now is that it's dominated by the error of the hadronic vacuum polarization contribution. So there are sort of two ways of determining this contribution, either from the experiments, from the R ratios with the dispersion relations. So that will be down here. That's just for the hadronic vacuum polarization contributions to a mu, or through lattice. This is a BMW result before it was published. It moved a little bit closer once it was published. So in other words, no. So the real question is, do we understand the theory, the standard model theory? The consensus numbers are rely mostly on the R ratios, and then the question is what is going on with the lattice prediction. The experiment went from the BNL one to the Fermilab. I changed the scale changed, so this band really shrank. You see that the two measurements are were consistent, and that's where we're getting the 4.2 sigma is by using the consensus standard model prediction, keeping in mind that the situation with the lattice predictions need to be resolved or further investigated. So these preliminary results. All right, so what I do is just say, okay, what happens if this is due to new physics? What does it mean? So so first of all, the experiment is above the standard model. It comes from a dimension 5 operator. So because it comes from dimension 5 operator, which is chirality flipping, I go from right-handed muon to a left-handed muon. There are two types of models that you can think of, new physics models that you can think of that would explain this. So if the chirality flipping comes from the external leg, so something like what's plotted here, so some new particles, but the chirality flipping is on the external leg, it can come from just one new degree of freedom. So this could be a muon instead of this generic S that is plotted here, plus, let's say, a light state, for instance, Z prime from L mu minus L tau. And when I say light, this is sub GeV, so 100 MeV or maybe 10 MeV. There is a region where this is still allowed. So these different, these grade regions are different constraints. This would be from the neutrino trident, or the Borexino is the scattering of neutrinos on the electrons. There is this green region that explains G minus 2, and with future neutrino experiments, you could cover a big chunk of it. All right, so that's the first set of models. So the second set of models is if the chirality flipping comes from the internal line, then you are no longer need to be suppressed by the muon Yukawa. So this coupling to the Higgs can be now enhanced large, depends on how much this new fermions couple to the Higgs, and the new physics can be much heavier. So what I'm showing here is an example where on top of G-2, you also try to explain the dark matter relic abundance. So one of the states that is running in the loop is charged, and the other one is dark matter candidate. If this is really a dark matter, it should lie on these lines. They depend on the parameters of the model. So essentially, these are the masses of the two states, up to some mixing contributions. The green band is where G-2 is. So you see now instead of 100 MeV, we're talking TeVs, so 1, 2, 3, 4 TeVs. And since this is a dark matter explanation, there are severe bounds from the direct detection, while the direct searches are not even touching at the G-2 of the muon region. All right, so that's as much as I wanted to say about G-2. So I'll move on to the next anomaly. So our set of anomalies, the B to S mu mu. So the upshot here is that just taking the theoretically clean observable, where it's very clear that we understand the error, you get the 5 sigma axis. Right, so that's really, I would say, big news. So if I say it in a different way, it's very unlikely that this is a problem in the theory predictions. If this is not new physics, there must be an experimental issue. It's consistent with many additional observers that require hadronic inputs. And on top of this, it's a relatively high new physics scale, as I said. So it's tens of TeV if the couplings are order 1. So it's less constrained by other probes like LHC searches. All right, so we'll go over the experimental situation quickly. I need a little bit of the notation. So in the standard model, these transitions are generated at one loop. If you integrate out the W, the Z, and the top, you will match onto an effective theory where the main contributions are due to these operators, dimension 6 operators, where we have B to S transition has a V minus A structure. And then whether it's a vector or an axial vector, the notation is that it's a C9 or a C10. So C9 means vector for the leptons, C10 means axial vector. And in the standard model, also the leptonic side is mostly V minus A. Now, the most important thing is that if you're well above the muon threshold, then the B to S E plus E minus and B to S mu plus mu minus should have exactly the same probabilities. This transition should have the same probabilities. So taking a ratio, you probe lepton flavor universality. And that's what's being done. So the observables that are being probed are either the ratio of B to K transition or B to K star. So both of these are B to S transitions where I either have a pseudoscalar or a vector, or a B sub S to mu plus mu minus. So all these are theoretically clean, well predicted. The measurements are in bins of 1 to 6 GeV and in 2 bins of B to K star. So if you look over the full spectrum, there are resonances that are cut out, and you sit below the resonance and you measure in a region where you're significantly above the threshold. So the LHCb measurement is here. It should be 1 if the standard model is correct, and the previous Babar and Bell measurements have significantly larger errors. The B to K star measurement hasn't changed in a long time. So these are 2 bins. This goes much closer to the muon threshold, the first one. So the standard model prediction that are colored here deviate from 1 just because of the muon mass effects, while in the higher bin they are consistent with 1. So that's in this region, and again you cut out the region with the resonances. So having a vector meson and a pseudoscalar meson in the final state is very useful in order to get to the chirality structure of the new physics. I'm just showing these two O9 and O10 operators. The primes here would be if you have a V plus A current on the quark side, while the scalar equivalents are already excluded by B2S, B sub S to mu mu. They would contribute much too much to the B sub S to mu mu. Now the fact that this K and K star have different parity then corresponds to having different linear combinations of this Wilson coefficient entering the ratio. So for instance, R sub K, you have this combination, while RK star has an extra, this is a polarization part, has an extra contribution just from the chirality structure. So seeing this visually, this is an odd plot, so the data are not exactly where they are now, but they're sort of in this region. It didn't change so much, just the error strength. So now if you switch on different chirality structures for the BSM, for instance, right-handed couplings on the quark side, but the left-handed on the leptonic side, you see that you're completely off. No? So in both cases, what you learn from these figures is that in both cases, you need left-handed couplings to quarks for new physics. Now, from the ratios, you can't tell whether the couplings are to the muons or the electrons. Right? So if you form, for instance, you could have a contribution which is right-handed on the quark side, right-handed on the electron side. This would still be fine let's plot it here. Okay, so that's where the B sub S, the mu mu enters. It's another precise clean observable. There's sort of a 2 sigma discrepancy between the standard model prediction. So this is showing B to mu mu versus B sub S mu mu, so both modes, and the different measurements by Atlas, LHCb, so Atlas and CMS. You see that the global combination is about 2 sigma away from the standard model. And this props just B sub S to mu mu, telling us that most likely, if this is new physics, it has to do with the muons. All right, so assuming that this is true, that we have couplings to muons, a fit to clean observables will give you a consistent picture. So that would be a fit to R sub K. And B sub S to mu mu, they overlap. And the comparison with the 2017, these are 3 sigma bands. Well, this is a 5 sigma contour. The inner one is the 3 sigma. You see that the old data and the new data are consistent and getting more significant. Another interesting thing is that there are many more observables that you can compare the standard model with the experiment. different branching ratios and angular observables. So for instance, I'm just showing two figures. For instance, you could have B to K mu plus mu minus either to electrons or muons. So while the electrons seem to agree with the standard model prediction, the muons seem to be lower. Notice that the standard model prediction has quite large error bands. That's why I call them the theoretically dirty. How large this error band is, it really depends on light consum rules, which is, you can always argue about the error bars there in these predictions. The same, for instance, for B sub s to phi mu plus mu minus. So all these measurements are sensitive to hadronic inputs. A celebrated one is, for instance, P5 prime, where so this would be the predictions for the standard model predictions are down here, while the experiments, the experimental data are above. Now, if you include all the nominal theory errors and do a global fit, you see that the clean fit, where you only use the clean observables, and the global fit, where you also include the so-called dirty observables, they do point to the same region in this Wilson coefficient parameter space. Now, there's so much data that now you can maybe start even relaxing the assumption about having physics only in the muon. So if you allow for a contribution which is universal, so both the electron and the muon have it, so this is CIU here, so C9U. That's the universal part for both muons and electron, and then a piece that is extra for the muons, sorry, V, no, so extra for the muons, which is in this case, the Barcelona group took C9, C9, this extra piece to be C9 is equal to minus C10. You see that there maybe is a hint for having a non-zero universal piece of coupling to the electrons as well. All right, so that's about the data. So what kind of new physics could we be talking about? So, these are, so we're, so all these Wilson coefficients had order 1 deviations in this normalization, where the normalization was in 36 TeV. So new physics will be order 40 TeV or so, if the couplings are order 1. So that means that you can have either tree-level contribution from new physics with smaller couplings, or loop level with larger couplings and lighter new physics. All right, so tree level can be, let's say, a Z prime that would mediate a transition, or a leptoquark, so we have B left to mu. Go maybe more quickly through those, since these have been around for quite a while. So the Z prime, probably the most celebrated example for a Z prime is a gauged mu minus L tau, where you induce the couplings to the quarks through some vector-like quarks that are much heavier. So you would have small couplings to the B left, so to the quarks due to this mixing suppression. This is something that is required phonologically because you don't need, you should not have large B sub s mixing contributions. So this induced coupling should be less than 1% if Z prime is at 2-3 TeV. The couplings to muons, if they have a left-handed component, then you also induce a neutrino trident signal. We have a neutrino scattering on a nucleus, and you see a mu plus mu minus production, where you have an extra contribution now from a Z prime. Now this leads to quite constrained parameter space for mu minus L tau. This was already chosen such that you explain the R sub k anomaly. So what's not excluded is in this white region where you can explain B sub s to mu plus mu minus. The LEPTOQUARKS there are 3 LEPTOQUARKS that can do the jobs. So you just look at whether they give you the right chirality structure, and out of the list of the LEPTOQUARKS, there will be the one that is a color triplet and a triplet of the SE2, or the vector, which is a color triplet, singlet of SE2, or a color triplet and a triplet of the SE2. Now here, the important thing is that the B sub S mixing imposes a constraint on how heavy these LEPTOQUARKS can be because of different scalings between the tree level contribution to B sub S to mu mu and the B sub S mixing, which scales as y to the 4 over m squared instead of y squared over m squared. And the bounds are depending on which one of these 3 guys you take. It's either 40, 45, or 20 TeV. There's an upper limit. I mentioned briefly these loop level induced models. Now, since you pay a loop factor, the new states are necessarily at a TeV or even less. And these are generally in tension with direct searches. So that's still a blank statement because nobody did a really detailed review of what the constraints are for all of them. But wherever people have looked recently, they're basically excluded these models. All right, so I'll now move on to the final anomaly, B2C tau nu, where, as remember, this is in the standard model, it is mediated by a W. It is theoretically clean as the 4 sigma-ish excess. However, the new physics effects are large. They're about 20% of the standard model at tree level. So that means that the new physics mass scale is really quite low, and the interpretations are more often than not in conflict with the other constraints, as we'll see. So the observables are, you take either the pseudoscalar or the vector, so D or D star. In the final state, you form a ratio where you have either a tau or a mu and an electron. And the standard model prediction has tiny errors, while the global average of Babar, Bell, and LHCb is away from the prediction. So this is RD versus RD star. Another thing which is maybe important to keep in mind psychologically is that which measurements drive the difference. So that's different measurements for RD star as a function of the submission date. And the discrepancies are really driven by the Babar data. So it's more recent Bell analysis somehow are much closer to the standard model. All right, so what kind of new physics could this point to? Now, what's observed is a missing energy because we have a transition with the neutrino in the final state. So if you assume that this is also just a standard model neutrino, then there's interference between the new physics and the standard model because they have the same final state. You could either have a W prime or a charge Higgs or LEPTOQUARKS. These most obvious candidates, which is I think before these anomalies were discovered experimentally, I would say most people would bet that this is going to discover a charge Higgs or W prime. These are excluded. Charge Higgs in many it violates many different observables. W prime also it's ruled out by the fact that there should be also Z prime. Z prime in the PP to tau tau, so a related high PT search. So more or less we're just left with the LEPTOQUARKS. Some of these are also ruled out. Now, if you contemplated that this missing energy is due to the right-handed neutrino, there's another set of models that you can write down. Some of them could be even more appealing. However, the scale is even lower because there's no interference with the standard model. So the nail in the coffin of many of these models is quite a model-independent constraint that comes from the following. So if you have a B2C tau nu transition that is showing anomalous behavior in the experimental measurements at low energies, there should be a related B2C annihilation, B and C, so B bar or C goes to tau nu annihilation, where you take a B from a proton, a C bar, let's say, from a proton, and you produce a tau nu final state. So the search for the PT dependence of the taus in a tau plus missing ET final state at the LHC has really severely constrained many of these models. For instance, these solutions with the right-handed neutrinos are ruled out, or more or less. So that's what's plotted here. Pick a mediator. Let's say we pick this U1 vector like quark. There's a tiny region here. In this red band means right-handed neutrino is assumed for the explanation of the anomaly. There's a tiny region here where this U1 is light. You have sort of reasonably small couplings to GC, GB, while the left-handed coupling solution would be probed with, let's say, high Lumi LHC. All right, so in the final 10 minutes or so, I wanted to say a little bit about if you start seeing a pattern in all these anomalies. So let's say if we try to see if these anomalies have anything to do with each other. So let's say if RK star and RD star are both found to be statistically significant, then so this is since these anomalies were around for a long time, let's say sort of there were quite a few analysis done. The vector-like LEPTOQUARK Q1 is a top candidate, I would say, in this respect. Or most people zoomed into that region. You could also solve it with two scalar LEPTOQUARKS, for instance. So the UV realization for the first one, there's a gauge 4321 model that I'll say a few words about. The other one, this S3, S1 could be a son of composite Higgs. If instead you discard the RD star, and let's say that only B sub S, B2S mu mu, and the G minus 2 are correct, then you can have either a LEPTOQUARK or some gauge symmetries, simplify dark matter in the loop, and so on. And then you could also attempt to do all three of them. I spend on each of these, I'll spend a little bit. All right, so RK and RK star, a similar table that I've shown is just for RK star. You can do for RD star. So plug in your different LEPTOQUARKS. You can either do or cannot do RD star and RK star. There's only one option which can do both, where one state dominates. The effective Lagrangian that you get if you integrate out this leptoquark has the following form. So, sorry, I misspoke. So the effective couplings of these leptoquarks will denote with these betas. When you integrate the U1 out, you get this effective C9, C10 Wilson coefficients. The switching on the, let's say, the right hand B right B tau to be -1 or 0, you'll get slightly different global fits for this B left S tau, B LD tau. This is where this line here denotes where a CKM-like structure. So if you just assume that these guys have CKM-like suppressions, this is where it would be on this green line, on this red line. So the flavor structure doesn't seem to be crazy. You could also search for those in the PP collisions. So that's what's already ruled out, are this great region. It's the mass of U. GU, I think with the flavor, this minimal flavor violation assumption, and that's where you would be at the high Lumi. The orange region is the solution where you have beta right, beta equal to 0. This solves the anomaly, so you would cover the whole region. So where could this come from? This so-called 4-3-2-1 model has all the necessary ingredients. So what you can notice is that if you combine, let's say, the leptons with the quarks, form of a 4 of the SU4, then you will have the U1 gauge bosons in here, in the part of the SU4, but there will be also a related color octet and another color singlet, Z prime, so GA and Z prime. The important thing here is that you can't, you should not be flavor universal, because if this is really a Patti Salam, then the KL to K long to mu plus E minus would exclude this possibility. So the bounds are much too severe. So the phonologically viable solution is where you only gauge the third generation. So SU4 only sees the third generation. And then you go through this series of breakings to the standard model. So in this breaking, in the TeV-ish scale, you get the U1 that you need for the anomaly, the color octets, the G prime, so the colorons, and the Z prime. So what you can now search for is all these gauge bosons. So for instance, not surprisingly, the most severe bound comes from the bounds on the colorons. So that's the present searches exclude. So that's the decay width of the coloron over the mass versus the mass. So these regions are excluded. Okay. So that the other option, for instance, was the RK star and G-2 of the muon. So here, I would say an interesting question is, can a single mediator explain both of these anomalies? Each separately, it's possible. So for instance, if you take the neutral spin 1 boson, X mu, the G-2 of the muon we already saw, so that we need 100 MeV, so definitely less than a GeV. For beta S mu plus mu minus, I didn't stress this, but it is also possible to explain it with a sort of light GeV-ish gauge boson, or if it's very heavy, which is what I was mostly talking about. However, even though these are kind of close, the solutions don't coincide, as you will see. So it's not possible to explain both G-2 of the muon and B2S mu plus mu minus at the same time with this spin 1 gauge boson. All right, so why does this happen? So the notation I'll use is the following. So I'll just switch on the low energy couplings that are needed for the two observables. So either couplings to muons, the vector and the axial. So if the vector and the axial are present, then the left-handed part of the muons will also have the muon neutrino, so the X will also couple to the muon neutrinos. And then let's switch on the couplings for the flavor of the diagonal B to S couplings, either the V minus A or the V plus A, so left-handed or right-handed currents. Now, if you look at G minus 2, doesn't matter whether this gauge boson, the X gauge boson is very light, less than the muon mass, or much heavier than the muon mass. In both cases, the contribution to G minus 2 will be positive only when the vector coupling is bigger than the axial coupling. This is the ratio of the muon over X mass. So this thing is only positive. So I need a positive contribution to the muon. Will give you the right some value for the gx, but that's not the important thing. The important thing is that this square root here, when I inverted the equation, needs to be positive. In other words, the vector coupling needs to be bigger than the axial one. Now, that has a very important consequence, which is that X mu necessarily couples to neutrinos. All right, so the fact that I cannot have a V minus A current, V plus A current. I necessarily have to have a V minus A component, means that I need couplings to neutrinos. All right, so a solution to G minus 2 implies that this vector couples to the neutrinos. And that is deadly, because if you try now to explain also B to S mu mu, then there are competing requirements. So the B to K nu bound will imply a small coupling for B to S. The neutrino trident will also imply a small coupling to the neutrinos. But I can't have both if I want to explain the anomaly. So that then numerically doesn't work. So I show this numerically. So what's plotted here is I take the mass of the this gauge boson versus the coupling Gx, and I need to fix the relative ratio between the axial and the vector couplings. This is where the B to K mu plus mu minus would be if you satisfy the B to K nu. The black region is where the G minus 2 of the muon wants it to be, and this grayed out region is where the neutrino trident constraints are. So no axial current. You see that we do have a region where the G minus 2 of the muon is explainable, which is already what we saw for L mu minus L tau, which would be an example of such a model. If you now switch on the axial coupling, so let's say switch on the axial coupling, make it negative, you see that slowly we require bigger and bigger gauge coupling, because the contributions to G minus 2 partially cancel. And at some point, they're just, the constraints from the neutrinos just become too stringent for G-2 to be even explainable by such a gauge boson. On the other hand, you saw that nothing was going on with R sub k region. If I make them positive, this is even more severe. All right, so in other words, you need, for the explanation of G-2, you need an almost vectorial coupling for x mu, and there's no way you can explain at the same time the b to s mu plus mu minus. Okay, so now we can do this a little bit more systematically. So that's what we did recently. Is you see that you need to extend the new physics, so there will be two states. What we did is we assumed that there will be an explanation for R sub k due to a leptoquark at 3 level, while G-2 comes from a gauge boson. Why this is useful is because if you gauge if you introduce a U1x, this can then explain why there are no mu to E gamma. So why there's such a hierarchy between the G-2 of the muon scale and the absence of mu to E gamma. The couplings can be, so these gauge couplings then can, first of all, fix the flavor structure so that the leptoquark will only couple to muons. So you can call them MUOQUARKS. There will be no flavor changing neutral current problems. I'll show is the universal charges for quarks. If you make them non-universal, you have to be much more careful. And at the same time, also the gauge charges can forbid fast proton decay, so no dimension 5 couplings. So there are many models in principle that now you can think of. I would say if we require that these gauge charges in the standard model plus 3 Riden and neutrinos are anomaly free, and just cut it off such that the ratios of different charges can be at most 10, then there are about 20 million solutions. This comes from Alanach and company. If you want to have a MUOQUARK, there are 273 models. So a large number, but they fall into not that many categories. So most of them are vector-like, so vector-like charges. And these vector-like charges are of two types. Either you have these sterile neutrinos have the same charges as the charged leptons, or you have this flipped version where any charges for 2 of the sterile neutrinos go if x mu is opposite to x tau. This is up to flavor permutations. There's also class 3 that I didn't put there, two vector-like charge assignments that don't fall into this category. And then in this car one, well, that's just the charged left-handed and the right-handed charges are not the same. There are about 10 of the remaining models. All right. So maybe it's a few benchmarks. So there are several relevant constraints here: neutrino trident, light resonance searches, and so on. So let me just show the LMU minus L tau, which clearly is one of the models. So that's this region that I've highlighted before that is not excluded by anything else. Another option would be LE minus L mu. It's the same thing. It's the same cancellation of the anomalies will happen if I have LE minus L mu. Well, in this case, since you're coupling to electrons, the bounds are much more severe. You see that this region is where G-2 could be explained is excluded. There's one wrinkle to this story is that if you allow kinetic mixing and fine tuning, so if you cancel at the percent level, then a viable, technically viable region would pop up. And then there are other possible benchmarks you can think of. I think I'll skip this. Um, you can also contemplate the combination of everything. So one thing that you can think of is you just take two leptoquarks that would, so two leptoquarks would explain three anomalies. A more minimal thing is, for instance, this paper by Marzoka, Trifinopoulos, where you can take an S1 leptoquark and a charged singlet. And the benefit here is that you can also resolve an anomaly that I didn't talk about, which is the Cabibbo angle anomaly, which is there's a discrepancy in the CKM unitarity in the first two rows. So VUS and VUD don't this. So VUS determinations and the VUD determinations don't seem to be in agreement. Depending on what you take for these nuclear beta decay elements, it's 3 or 5 sigma. And just with these two new states, you can explain RK star, G-2, and this Cabibbo anomaly. Now here you would predict a B to K star nu and B to K mu E signal, which can be probed by BER2 and LHCb. So these are these two lines here. That's the present, and these are the regions where you explain the anomalies. I'm a bit over time, so I have 3 slides about the future. I think the main thing is I won't really go into too much details. The main thing is that there's many measurements that you can do. There are sort of 2 types. Either you search in at low energies, improve the measurements of the anomalies, make sure that these measurements are coming from not just LHCb, but once BER2 starts seeing things. So BER2 just started taking data a year ago. If they confirm these anomalies, I think then we're basically in business. LFCB also has an upgrade program, set 30 times, 100 times statistics. There's also a muon G-2 at the J Park. So again, there will be a completely new experiment. So that's the sort of low energy observables that you can improve on. But then all these states you can search for at the high PT program. So some of these point to a TV scale. So Atlas and CMS have a good shot. If the couplings are order 1, then we're at 40 TV, then we're looking at 100 TV PP. So I'll show just maybe 2, I think. So BER2, this is really a drastic improvement in the error bars is envisioned. This is for R sub K. The LHCb, this is where we are in the RK star phi, and this is where we can be after the second upgrade. So this will translate into really a drastically improved. So this doesn't even show run 1. So run 3 versus upgrade 2 would also be a big jump when you talk about the constraints and the Wilson coefficients, if you can get the theoretical errors also done. All right, so I'm done. So what I talked about is first part was more general. So just a general statement means that these flavor changing neutral currents are very sensitive probes of new physics. What this means is that we should not be surprised if this is the first place where we see deviations, because in principle we are probing quite high scales. And then I talked mostly about this growing tension in the G-2 of the muon and RK star. I dropped the RD. And the main question is whether this is an evidence of new physics.
Okay, so thanks a lot, Jure, for this very comprehensive and pedagogical presentation. Now I wish to open the floor for comments, questions. Whoever wishes to say anything, please raise your hand through the reactions button in Zoom. Okay, maybe I can say something. So, Jure, could you possibly comment on the models for Z prime? Because we heard in talks by Claudia Fujuel and Caterina yesterday that the Z prime also plays a role in dark matter and dark sector searches. We also have these limits set by the LFC experiments on Z prime at the TV scales, mostly based on U1 prime gauge groups, how they connect with the Z prime models, which are used for explaining the B anomalies.
Yeah, that's a good question. I can't go back. See, I don't know if I even want to show. So there are actually packed into this quite a few questions in reality. So the thing is that, maybe I'll go to the Z prime for the BCBS here. So we at least look at something. So there are, yeah, I think there is no direct relation to the dark matter. I don't know what was said, what Claudia was talking about this morning. In principle, it doesn't have to be any direct relation. And of course, you can have just tag on an extra state, which is a dark matter one, and then you couple to the Z prime. I would say that when you do that, there will be really two different regimes, depending on whether the Z prime is very light or very heavy. So are you probing it with LHC or not? For instance, so this will have to do less with the dark matter, but more with the anomalies themselves. If Z prime is light and couples to muons, there was this idea that you could see a deviation also in the muon spectrum at the LHC. Now it turns out that unless you fine-tune dimension 6 against dimension 8 couplings, you will necessarily also have couplings to neutrinos, and then the LHC there's no signal at LHC. No, just this neutrino tridents that I'm showing here just completely kill the region that you could probe with the LHC. So you have to tune this away. Now this has nothing to do with dark matter. Dark matter is, I would say, is you can bring in two ways. For instance, if it contributes to G-2, that is kind of more natural because it enters at one. If it enters at one loop, now there's a Z2 that you can think of that is odd. So that would explain why dark matter is stable and why it contributes at one loop, which is the size that you need for G-2. If it's just an extra state that you couple to the Z prime, then I think there are many options that are open. No? And then it's a what if question. So I think whatever Claudia was talking you about, I'm sure that okay. I mean, honestly, I don't know whether you can really put any constraints from the anomalies. Yeah, sorry. The slides are not online, so it's not entirely my fault that I don't know what
No,
you're
but I
talking
also
about.
meant to say, I mean, of course, your Z prime,
Yes.
I mean, the Z prime in favor of physics used for explaining the anomaly is not the Z prime on which ATOS and CMS set a cut of 4 TV or something like that. I mean, which is a U1 prime Z prime. Otherwise, you wouldn't
Exactly. Yeah, exactly.
discuss a Z prime of the order of 10 GV or 100 GV, which as you have in this plot. So this is what I just meant. Yes. And also, I mean, Claudio was also talking of light Z prime decaying to dark photons and so on. Okay.
Yeah, so that's the thing. Yeah, exactly. The light Z prime. No, so I suspected that. That's why I made this comment. The light Z prime. You know, unless you buy into this really fine-tune, I don't know how to even write a UV model that would give me this couplings. No, it's dimension 6, and then I put 2 more insertions of the Higgs, and I can cancel these 2 operators have nothing to do with each other. This would, for instance, you could potentially have a Z prime signal at the LHC from the recoils, no? Against the muons. But apart from that, no, it's much more just directly searching for a Z prime, BS to Z prime will give you a bound, but the couplings are tiny, no, they're small. No, I mean there's this G prime times 10 to the -2 suppression. No?
Okay.
That's the problem. No?
Okay, thank you. I see that David has a question or a comment. If you can hear me, David Denteria has a comment. He has raised his hand.
You cannot. Can you hear me now?
Yes, now we can hear you. Thank you. Go ahead.
Sorry, I was trying to make my microphone work. I was wondering, I don't know if you discuss it because I've been following that talk a little bit fragmentally because of family issues here at home. But I was wondering if CMS has measured recently the ratios of branching ratio of W to leptons, electron, muon, and tau, and they are consistent with 1. So there is no within 1%, 2%, all these ratios are consistent. I was wondering if this allows to place some constraints on any of these BSM limits for processes that go through the W boson.
Yeah, I mean, you're talking about there used to be a discrepancy there for W to tau.
Yes, but this has disappeared. Yeah, this was at lab time. Exactly. This has disappeared. Yes.
Right, and that was, I mean, in a way, it was very hard to write down models for that already before, because as long as this matched onto an EFT, I mean, it was gone. No, you couldn't do it. There were other constraints. So the only place that you could imagine writing a model for that thing was that you would have a state which would be close to a W. No? So, for instance, a charged Higgs, no? That somehow you don't see. I think for the anomalies, so, you know, since this is now a very low scale, this is really was completely ruled out by other observers already, I think. Unless, okay, there's always a wrinkle there now, which would be that if you were looking at a very broad state, then the low energy observers would not be, I mean, you just can't relate. No? So low energy observers would be there, but you wouldn't see anything except for a very broad thing at at the collider, so super wide resonance. That would also not enter this measurement, no? Because you demand the W prime. I think, okay, I'm not 100%. That's my gut feeling, is that I'm not sure it would even would pass. I don't know, to be honest. So there's this wrinkle where you're in the non-perturbative regime and it's hard to evaluate.
My question, maybe phrase it otherwise, is if there is lepton flavor violation in universality, lepton flavor universality violation, what would, in one of these anomalies that we observe, shouldn't we see it also in WD case also at some point?
Yes. Yeah, I'm not sure actually. I mean, for sure. I mean, at one loop, yes, but this is too tiny, you know. So, not okay. Not sure. It's definitely not something that sounds like where you would first. I mean, that you could. Maybe I'm too naive, but that's. I think it's not. It doesn't look like it. No.
Okay, thank you.
Yeah.
Okay, is there any other comment or question? Please raise your hand.
Because yeah, maybe I say a bit more now. For instance, this here now when I talked about the, that's kind of relaxed. Let me see. For instance, now just that we have a feel for the precision that is needed. Now, so this guy here, the last thing that I was talking about is the discrepancy, the Kabiba angle discrepancy. Right? So you see that this is a contribution to a W, effectively, no? Or so this is a measurement of the G Fermi in the muon case. No? So yes, there would be a lepton universality violation from this one loop contribution. But you need to compare this with what this does in the G Fermi. You know? It's a super precise measurement, and it just barely switches. Barely, you know? That's what we're talking about now. So one loop, no? One loop here, and so it would be there. I mean, maybe it's worth checking, no, just to make sure that I'm not naively guessing what the size is. I can check if you're interested.
Okay, thanks for
yeah.
the explanation, for answering.